You can write a real GPU kernel today with zero CUDA installed, right now. No NVCC, no QBLS. Same file runs on NVIDIA, AMD, and Apple Silicon. This is Modular's real claim, and it holds up. You write one Mojo file. It compiles straight to NVIDIA, AMD, or Apple Silicon GPU code, no vendor-specific rewrite required. You never touch NVCC. You never link QBLAS or CUDNN. That's the whole CUDA toolkit, gone from your workflow. The project isn't some weekend side thing either. Modular's GitHub repo sits at 26 K-stars and 2,895 forks, with commits landing as recently as yesterday. That's real signal for how much active work is going into this, not just marketing. This is a fast-moving, actively maintained compiler, not an abandoned experiment. Here's the catch nobody puts in the headline. No CUDA means no CUDA toolkit, not no NVIDIA software at all. Target an NVIDIA card, and you still need NVIDIA's own driver, version 580 or newer, because Mojo still lowers to PTX under the hood for NVIDIA targets. AMD needs ROCm 6.3.3 or newer, and Modular's newest chip, the MI355X, specifically needs ROCm 7.0. Apple Silicon needs Xcode 16, and macOS Sequoia 15. Every vendor's driver stack is still a hard requirement. None of that is optional, and none of it is CUDA. It's each vendor's own driver, doing what drivers always did. Mojo replaces the toolkit. It doesn't replace the hardware vendor. Here's what actually works, vendor by vendor. On NVIDIA, anything from the RTX 30 series up is known compatible, along with the H100 and the newer B200. If you're on a gaming laptop or desktop, there's a good chance you already qualify. RTX 3060, RTX 4060, anything in that consumer bracket falls into known compatible, no exotic data center card required. On AMD, MI300X and MI355X are continuously tested, and consumer cards like the RX 7900 and RX 9070 work too. On Apple Silicon, M1 through M5 chips are all known compatible for GPU programming, though large model inference through Max is a separate gap that doesn't affect this tutorial. One thing that's dropped, pre-Turing NVIDIA cards, like the GTX 10 series, aren't supported out of the box anymore. One more honest beat. If you've got no supported GPU, the tutorial's own example doesn't quietly fall back to your CPU. It calls Hasistra Accelerator at compile time, and if that comes back false, it just prints no compatible GPU found and stops. No vector addition happens, no numbers get computed. Mojo's runtime does have general driver loading fallback logic elsewhere in the stack, but this specific example isn't using it, so don't expect it to just work on a CPU-only laptop. It's a real limitation worth knowing before you spend an afternoon debugging why nothing prints. Getting it installed is 2 commands if you use UV. Install UV itself, then run UV pip install Mojo with the pre-release allow flag, since 1.0 is still in beta. Run Mojo- version afterward, and you should see 1.0.0b2, which is part of Modular Platform 26.4, released June 18th, 2026. That pre-release flag isn't a permanent requirement. It exists specifically because Mojo 1.0 hasn't shipped yet. Nightly builds are already a step ahead. Dev tags like 1.0.0b3 showed up just 3 days before this was written. There's a second path too. Pixie, the tool the official GPU tutorial actually uses, which sets up a project folder and drops you into a shell with Mojo add. Either way, you're not touching CUDA's installer at any point. Here's the actual kernel function. About 15 lines, and every GPU thread runs the same code at once. Each thread computes its own global index. Block index times block dimension plus thread index. That's the identical math CUDA uses under a different name. I post one of these every day. Subscribe if this kind of build along is useful. Every one of those pieces, block IDX, block dim, thread IDX, is Mojo's own name for a CUDA concept. Thread IDX and block IDX, renamed, same idea underneath. Then comes the bounds guard. If that index is less than the vector size, add the 2 numbers and store the result. Skip that guard, and threads pass the end of your data read and write garbage. Threads sit inside blocks. Blocks sit inside a grid. This vector has 1,000 elements, and each block holds 256 threads, so you need 4 blocks to cover it, which launches 224 threads total. That's 24 threads more than you actually have data for. GPUs always round up to full blocks like this. That's because GPUs schedule threads in fixed size groups called warps, not one at a time, so the hardware always rounds block sizes up to full groups. Without the bounds check from the last scene, those 24 extra threads would read and write past the end of your buffer, and your kernel could crash or just return garbage. The host side code around the kernel is ordinary Mojo, not a separate language. You create a device context, allocate host and device buffers, and copy the 2 input arrays over within QCopy. It fills the left buffer with 0 up to 999, and the right buffer with half of that. So index I holds I on the left, and I times 0.5 on the right, values you'll check by hand in a minute. Then you launch the kernel itself within Q function, passing grid dim as 4 blocks, and block dim as 256 threads, the exact numbers from the last diagram. Run it with a single command, mojo vector addition, .mojo. There's no separate compile step, no building a binary first. It compiles and executes in one shot. You get 3 lines back, the left-hand buffer, the right-hand buffer, and the result, each one truncated with dots in the middle, since printing all 1,000 values would be unreadable. Check the last value by hand. Index 9999, left is 9999, right is 499.5. Add them and you get 1,498.5, the exact number the GPU printed. Try index 02, left is 0, right is 0, result is 0. The pattern holds at both ends of the buffer, not just the one value we picked. The kernel actually did the math on real GPU hardware, not a simulation, and you can verify every single one of the 1,000 values the same way. Modular has a real measured number here, not marketing copy. A from-scratch Mojo kernel for NF4 dequantization beat Unsloth's handwritten CUDA kernel on every GPU tested. On a T4, 1.07x faster. On an L4, 1.25x. On an A100, 1.84x. On an H100, 1.51x. The author's own line, Mojo's advantage is that it stays out of your way. That's modular published and community authored, so treat it as self-reported, not independently audited. An outside check exists too. Oak Ridge researchers benchmarked Mojo against CUDA on an H100 across 4 HPC kernels and found Mojo running at about 87% of CUDA's speed on average, faster on some, like Babelstream and MiniBude, and slower on others, like Dot Product, at roughly 78%. Zoom out and there's a bigger story here. Qualcomm is acquiring Modular for about $3.90 billion, announced June 24th, 2026, explicitly framed by both companies as a move against NVIDIA's CUDA moat. That deal hasn't closed yet. It's pending regulatory review through the second half of 2026. And Mojo's compiler still isn't open source. It runs under the Modular Community License, with open sourcing committed for fall 2026, but not shipped. The standard library is already open, Apache 2.0 since March 2024. It's the compiler itself that's still locked behind Modular's license. So the actual trade-off is this. You get one file that targets 3 GPU vendors with 0 rewrites, but you're building on beta software, version 1.0.0b2, from a company mid-acquisition that CUDA C, after 18 years, simply doesn't have to worry about. Mojo's GPU story is real. One file, 3 vendors, an actual kernel that runs and checks out by hand. It's also beta software from a company in the middle of a $3.90 billion acquisition, with an open source promise that hasn't landed yet. Try the tutorial yourself, and keep an eye on that fall 2026 date.